Have you ever looked up at the night sky? Have you ever wondered about the stars twinkling back at you? Each one is a distant sun, a giant ball of burning gas. Most live for billions of years, shining steadily. But some stars have a much more dramatic end. They don't just fade away quietly into the darkness. Instead, they go out with a bang, a really, really big bang. These explosions are some of the most powerful events in the entire universe. They can outshine entire galaxies for a short time. Imagine a single light bulb suddenly becoming brighter than all the lights in a major city combined. That's what we're talking about here, on a truly cosmic scale. So, what do you call an explosion that makes a supernova look like a small firecracker? You need a new word. You need a word that captures its sheer mind-boggling scale. Astronomers came up with the perfect name, a hypernova. The prefix hyper means over, beyond, or excessive. And that's exactly what a hypernova is. It is an explosion that goes far beyond the already incredible power of a regular supernova. It's not just a little bit more powerful. It is orders of magnitude more energetic. Imagine a standard supernova as a massive stick of dynamite. It's powerful enough to level a building. Now imagine a hypernova as a nuclear bomb. The difference in scale is immense. The story of the hypernova is a story of scientific discovery. It's a tale of seeing something you can't explain and chasing the mystery. But then, in the 1990s, things started to get strange. Astronomers observed a few supernovae that were just wrong. They were too bright. They were too powerful. One famous example was a supernova called SN 1998BW. It was unlike anything seen before. This particular supernova was linked to a gamma-ray burst. That was the first big clue. Gamma-ray bursts, or GRBs, were a puzzle in themselves. They were detected by military satellites looking for secret nuclear tests in the 1960s. But these bursts were coming from outer space. To truly understand what makes a hypernova so special, we first need to look at its smaller cousin. We need to get to know the supernova. For a star to go supernova, it needs one key ingredient: mass. Not just any star can do it. Our sun, for example, is too small. These massive stars live their lives in a constant battle against gravity. Their immense mass creates an incredible gravitational pull trying to crush the star inwards. What holds gravity at bay is the energy produced by nuclear fusion in the star's core. For millions of years, the star fuses lighter elements into heavier ones, like hydrogen into helium, then helium into carbon and oxygen. The star develops an onion-like structure, with different elements fusing in concentric shells around the core. Iron is the end of the line. Fusing iron into heavier elements doesn't release energy, it consumes it. When the core becomes filled with iron, the star's energy source is cut off. With nothing left to hold it up, gravity wins the war. The iron core collapses in on itself in less than a second. Now, when we talk about supernovae, it's a bit like talking about cars. There isn't just one type. The two main families are type 1 and type 2. The easiest way to tell them apart is by looking for hydrogen. Type 2 supernovae have lots of hydrogen visible in the light they emit, while type 1 supernovae have none. The type 2 supernova is the classic story we just discussed. It's the death of a single, massive star that still has its outer layers of hydrogen intact when it explodes. Type 1 supernovae are more mysterious. The most famous subcategory is the type Ia supernova. This one doesn't come from a massive star at all. It comes from the dead, compact remnant of a star like our sun, a white dwarf. Supernovae are more than just spectacular light shows. They are the universe's ultimate factories. They are responsible for creating many of the heavier elements that make up the world around us. During a star's normal life, its fusion core can only create elements up to iron. But what about everything else? Where do elements like gold, platinum, silver, and uranium come from? The moment the star's core collapses and the shockwave rips through its outer layers, the conditions become truly extreme. This intense environment is the perfect furnace for creating the heaviest elements in the periodic table. So the gold in a wedding ring, the silver in a coin, the uranium that powers nuclear reactors, all of it was born in the heart of a supernova explosion. Supernovae don't just enrich the cosmos with heavy elements, they actively trigger the birth of new stars and planets. The shockwave from a supernova explosion crashes into the vast, cold clouds of gas and dust that drift through the galaxy. As this wave of energy and pressure sweeps through a molecular cloud, it compresses the gas and dust. It creates dense pockets and knots within the cloud. Once these pockets become dense enough, their own gravity takes over. Eventually, the core of one of these collapsing clumps becomes so hot and dense that nuclear fusion ignites. A new star is born. Our own sun and solar system were likely born this way. It's a beautiful cycle of cosmic life and death. The death of one massive star provides the raw materials and the trigger for the birth of a new generation of stars and planetary systems. So we have a good picture of a supernova. For a long time, we thought this was the biggest bang the universe had to offer. But the cosmos had a surprise waiting for us. Astronomers started seeing explosions that were simply off the charts. They were so powerful, so luminous, that the word super just didn't do them justice. Let's try to get a sense of the scale we are talking about. Imagine a supernova is a powerful bolt of lightning. A hypernova, by comparison, is like harnessing the entire power output of a major city's electrical grid and releasing it all in a single, blinding millisecond. For a few weeks, a single hypernova can outshine its host galaxy, which might contain hundreds of billions of other stars. If a hypernova were to happen on the other side of our own Milky Way galaxy, it would still be one of the brightest objects in our night sky. How is a hypernova different from a regular supernova? On the surface, they might look similar. Both involve the collapse of a massive star's core. But the key differences lie deep within the dying star. While a supernova often leaves behind a neutron star, a hypernova is so powerful that it creates something even more extreme. It forges something with a gravitational pull so strong that not even light can escape, a black hole. The formation of this new black hole changes everything. As the rest of the star's material rains down onto this newborn monster, it forms a swirling, superheated disk of matter around it. This is called an accretion disk. The friction and magnetic fields within this disk heat the material to billions of degrees. This process releases an absolutely colossal amount of energy, far more than the simple shockwave of a normal supernova could ever produce. The birth of a black hole at the heart of a dying star is a game changer. The real secret to its power lies in how that black hole unleashes its energy. It doesn't just radiate heat in all directions like a light bulb. Instead, it focuses its energy into two narrow, incredibly powerful beams of matter and radiation. These beams are called relativistic jets. They are like cosmic blowtorches, blasting their way out from the poles of the collapsing star at nearly the speed of light. This, combined with unbelievably strong magnetic fields, creates a kind of cosmic funnel. This funnel takes the raw energy being released by the disk and channels it outwards along the black hole's axis of rotation. If one of these hypernova jets happens to be pointed directly at Earth, we see that intense beam of energy as a long-duration gamma-ray burst. We are, in effect, staring right down the barrel of a cosmic gun. So we now have two key ingredients for a hypernova, a truly massive star, and the formation of a black hole. But there's still one more crucial piece to the puzzle. The star needs something extra. It needs to be spinning. Think about what happens when an ice skater pulls their arms in. They spin faster. That's called the conservation of angular momentum. The same principle applies to a collapsing star, but on a cosmic scale. So, why do some massive stars spin so fast? One leading idea is that these stars are born in binary systems orbiting closely with another star. The gravitational dance between the two stars can spin the primary star up. This metallicity connection suggests that hypernovae were much more common in the early universe. These primordial hypernova would have played a crucial role in shaping the early universe, producing the first black holes and scattering the first batches of heavy elements. The story of how we discovered hypernovae isn't a simple tale of an astronomer looking through a telescope. One of the most important clues actually came not from astronomy, but from the Cold War. Back in the 1960s, the United States launched a series of satellites called Vela. Their mission was secret. They were designed to watch for gamma rays that would signal a forbidden nuclear bomb test in space by the Soviet Union. The satellites did their job well, but then they started seeing flashes of gamma rays that weren't coming from Earth. They were coming from deep space. These flashes were a complete mystery. The data was classified for years, but when it was finally released to the scientific community in 1973, it sparked a decades-long puzzle. Astronomers called them gamma-ray bursts, or GRBs. The key that unlocked the mystery of gamma-ray bursts was the ability to find them quickly. In 1997, an Italian-Dutch satellite named BeppoSat did just that. On February 28, 1997, it hit the jackpot. BeppoSat detected a burst and swiftly relayed its coordinates to ground-based observatories. For the first time, we could see the afterglow. Astronomers scrambled to point their most powerful telescopes at the fading embers of the explosion. The afterglows of these GRBs were often found in the bright star-forming regions of their host galaxies. This was a significant clue. The idea of a supernova being involved grew stronger. But there was a problem. A normal supernova just didn't seem to have enough energy to create a GRB that could be seen from so far away. This is when the idea of a hypernova really began to take shape. The definitive proof, the so-called smoking gun that connected gamma-ray bursts to a new super-powerful class of supernova, arrived just over a year later. On April 25, 1998, BeppoSat detected another gamma-ray burst, GRB 980425. This one was different. It was much closer than any burst seen before. Just days after the burst, astronomers discovered a brilliant exploding star, a supernova, in the exact same location as the gamma-ray burst. They named it SN 1998BW. For the first time, a GRB had been directly linked to a supernova explosion. But when scientists analyzed the supernova itself, they realized it was very strange. It was incredibly bright, much more luminous than a typical core collapse supernova. It had all the hallmarks of the theoretical hypernova that scientists had proposed. Here was the physical evidence. The GRB was the flash from the cosmic cannon, and SN 1998BW was the massive exploding cannonball itself. With the groundbreaking discovery of SN 1998BW, scientists had the crucial evidence they needed. Now, they could confidently refine the theory that explained it all, the Collapsar model. Scientists predicted that because the explosion was driven by jets, it wouldn't be a perfect sphere. Using sophisticated techniques to measure the polarization of light from these explosions, astronomers were able to confirm this. The model also explained why GRBs seem so rare. The jets are narrow. You have to be looking right down the barrel of one to see the gamma-ray burst. For every one GRB we see, there could be hundreds of other hypernovae exploding where the jets are pointed in other directions. The discovery of hypernovae and the development of the Collapsar model represent a huge leap in our understanding. From the secret Vela satellites to the detailed study of a single strange supernova, the scientific community unraveled a cosmic mystery. So we've explored what hypernovae are and how they were discovered. But why do they matter? The answer is a resounding no to them being just distant fireworks. They are fundamental actors on the cosmic stage. Their immense power has immense consequences. While a regular supernova shockwave can trigger star formation, a hypernova's shockwave is so ferocious that it can completely blow away stellar nurseries, creating superbubbles that stretch for thousands of light years. Furthermore, hypernovae are incredibly effective at enriching their host galaxies with heavy elements. Because the explosion is so much more energetic, it flings the newly forged elements much farther and faster into space. While a supernova seeds its local neighborhood, a hypernova can blast heavy elements clear out of a small dwarf galaxy and into the void between galaxies. They are the universe's most powerful distribution network. One of the most profound roles of a hypernova is what it leaves behind. Every time a hypernova explodes, it seeds the universe with another stellar mass black hole. These black holes are the seeds from which bigger things can grow. It is now widely believed that the supermassive black holes found at the center of nearly every large galaxy grew from these smaller seeds. Primordial hypernovae in the early universe would have created the first generation of black holes. The black holes created by hypernovae are also special. Because they are born from rapidly spinning stars, these black holes are themselves likely to be spinning incredibly fast. A spinning black hole has very different properties to a non-spinning one. This spin contains a tremendous amount of rotational energy, which can be extracted to power other spectacular cosmic phenomena. A spinning black hole is a long-lasting cosmic battery, capable of powering jets and other high-energy events for billions of years. Perhaps the most exciting reason hypernovae are important to scientists is their role as cosmic lighthouses. Because they are so incredibly bright, they can be seen from astonishing distances. This means we can detect them in the far reaches of the cosmos, looking back in time to when the universe was much younger. Each distant hypernova we find is like a message in a bottle from the past. When we look at a hypernova that is 10 billion light years away, we are seeing the light from an explosion that happened 10 billion years ago. By analyzing the light from that hypernova, we can learn about the environment it exploded in. This is why powerful new observatories like the James Webb Space Telescope are so focused on hunting for these distant flashes. Each one is a clue, a piece of the puzzle that helps us reconstruct the story of our cosmic origins. We have journeyed to the most violent corners of the cosmos. We've explored the death of the universe's most massive stars. We've seen how a standard supernova is dwarfed by the fury of its bigger cousin, the hypernova. The Collapsar model gives us a stunningly elegant picture. It all starts with a true giant spinning furiously. When the star runs out of fuel, it keeps on crushing, forging a spinning black hole that becomes the engine of destruction. Yet, for all we have learned, the frontier of our knowledge continues to expand. We're still asking profound questions about these cosmic titans. Just how massive can a star get before it collapses? What are the precise conditions that trigger a hypernova? Each answer we find only opens up new, more detailed questions. This is the beauty of science. It is not a destination, but a journey, a continuous process of discovery that takes us ever deeper into the workings of the cosmos. The study of hypernovae reminds us that the universe is far more extreme and dynamic than we can easily imagine. We live on a quiet, peaceful planet, orbiting a stable, well-behaved star. These cosmic beacons also connect us to our own deep past. The iron in your blood, the calcium in your bones, the gold in a ring, these elements were forged in the hearts of stars and scattered by explosions like hypernovae. So the next time you look up at the night sky, take a moment to think about what you are really seeing. You are looking at a vast and dynamic universe, a place of constant change. And out there, in distant galaxies far too faint to see with your eyes, hypernovae are exploding right now. They are lighting up the cosmos, forging new elements, creating black holes, and sending messages to us across billions of years of time and space. This is why we explore. We're driven by an innate need to understand our place in the universe. The universe is full of wonders, from the smallest particles to the largest explosions. There are still so many mysteries waiting to be solved, so many discoveries waiting to be made. The story of the hypernova is just one chapter in an infinite book, and the best part is, we get to keep turning the pages. The journey is far from over.